can let me know in the ping. So recording has already been started for everyone. I will request everyone to please keep yourself on mute. And with that, Ayushman, a warm welcome to you again, and over to you now. Thanks. Thanks.
Thanks a lot, Jainendra, for the warm welcome. And it's a pleasure for me to be here. I have always loved teaching. I used to also take a few classes when I was in grad school, and I really miss going back to classrooms and teaching classes. So it makes me feel a bit nostalgic as well. So, so everyone, a lot of people here. Thanks a lot for joining. It's early morning in Delhi as well. I think a lot of you guys are in Delhi, so I can understand your pain. Although I am a big fan of Delhi winters. From the coast, I was born and brought up here, and I've always been in warm weathers. So I'll give a quick intro to myself. I think Janendra did a wonderful job, but a little bit of background that I'm a musician. I think I'm a musician who loves AI and language processing. I built NLP tools for over 80 languages. I've been in various geographies, started in India, went to Germany, worked on various European languages over there, then moved to Canada, worked on French and various other languages like French, Spanish, English, etc. over there as well, including one of the languages called Inuktitut. I don't know if you guys have ever heard of such a language, but it's a very rare language which does not have spaces. So their sentences are like 80 characters long or 90 characters long. So I've worked with a lot of languages, and hence my love for languages comes from all my experience and all the journey and culture that I've seen all over the world. I'm a big supporter of NLP for low resource languages. I try to collaborate with people and try to bring NLP for low resource languages out there. And I'm a traveler. I've traveled over 14 countries and I'm still counting. I love to explore cultures, learn about languages, learn about how people have come to such a point where we are speaking. I think all of you are aware of the fact that we are mixing English with our native tongue, and we are coming up with new languages like English, Benglish, Tenglish, etc. So currently one of my interests are to understand how did we even come up with such a thing, and how is it becoming a new language of the internet. So yeah, that's me, and I'm the CTO and co-founder of Neurospace. So without any further ado, I will kickstart this. I don't want to call it a lecture. I would rather call it a talk on finding potential mining sites for naturally occurring metals using explainable NLP. So a lot of you must be thinking that how can you use NLP to find mining sites? That sounds a bit counterintuitive, intuitive, right? So if I would have said that using explainable computer vision or something like that, then you would have been like, okay, maybe we are using satellite images and then trying to find out mining sites from here and there. But I'm going to tell you how we used NLP and how it was a big challenge for the government of Canada, and how we could help them in overcoming this challenge. Um, all right. So part one of this talk is the problem. The problem was brought to us by Natural Resources Canada when I was working at Element AI. We were a team of three. We were working as machine learning consultants there. What Natural Resources Canada was finding very difficult to do was I'm sorry. So what they were finding difficult to do is that so every time they would go to mine a certain metal or a certain ore, they had to go through a very long and manual process, which not only included people going to the mining sites, but a lot of manual process happened before even people went to the mining sites and tested out the land and saw what is actually in there, which involved a lot of research, going through archive papers, reading papers from all over the world. So doing all of that through domain experts is a very, very expensive process. And I'm going to talk a little bit about that in a bit. So what we did, so the problem was that how can we reduce the manual effort over there? And also how can we find these mining sites from a lot of archived documents, as well as documents being recently published on the internet or various forums or journals. That was the problem statement that they had. But I'll give you a little bit of backstory. So the world runs on metal. There's no question about that. And we all are holding a piece of metal right now in front of us. So how do we get so much metal? We mine them. We go to mining sites, we dig holes, and then we find these metals, these ores, and then there is a lot of refinement process that happens after that. Sadly, I could not. The only pictures I could get was open cast mining, but there are different kinds of mining activities that can happen in the world. But in this case, I'm just showing open cast mining. So for mining, for the entire effort to work out, usually people start with research, or geologists, they start with research. That means they would go through various geochemistry or geology papers, study from the past, which is archived papers, and note that we are talking about a field which is geology, and they are technically not that savvy, right? So technology in terms of cloud services, search, etc., it has not advanced so much. Some countries are uh, ahead of some other countries, but again, overall, they are not that advanced. So doing all these searches are mostly keyword searches, to find out which papers are relevant, which papers are not relevant, and literally tens or 15 10 or 15 domain experts have to sit down for each project and go through these papers manually day in and day out. They spend hours doing this, and then come up with these papers which are more relevant, which talk about geological sites or geographical sites, which mine certain metals or ores. So once they are done with that, they start an exploration phase. So they would send people who would go to that geographical location. They would take samples. They try to figure out what's there in this land. But again, when we are talking about ores, right? So when we are talking about mining a certain metal, they come from a certain ore. And when we talk about ores, we need to understand that it has to be economically feasible as well. It's not that if let's say gold is available here, let's start mining it. That's almost never the case, unless it's a very rare event. So that's why it has to be economical as well. So they have to go from one place to the other and then figure out which of these geographical locations are actually good for mining and which are economically feasible. Exploration is also a very expensive process. Once that is done, then they do something called mapping. So mapping is where they do some sort of feasibility analysis. They collect samples, they prepare charts, they prepare reports, they also map the geographical locations and find out potential return on investment. That means if we spend X amount of money, how much metal are we going to get from there, and then how are we going to sell it? So that is done during the mapping phase. And after that, huge machines are bought. You'd be surprised how expensive they are. Some of these machines that are used for mining are more than half a million US dollars. And I'm just talking about some of these machines, and then the whole crew has to go there, and there is maintenance cost, and then plus they have to also nowadays, that people are aware that mining does a lot of harm to the environment. People have to spend for offsetting what harm they have done already, right? So it's a huge expense, that there's a lot of money that goes into this. So the reason why I'm talking about all this is that one of the reasons why NRCan, or Natural Resources Canada, wanted to do this activity was to kind of reduce the research, exploration, and mapping expense, because the mining expense they cannot reduce. They have to spend that money. But can we reduce our expenses when it comes to research, exploration, and mapping? That was the question that they had. So the problem is that there are thousands of research papers that come almost every other day. Manual keyword search has really, really low precision, which is around 20 to 30%. This is what we were told at that time. It has 20 to 30% precision. And a lot of papers, very important papers, are also lost in the process, is because maybe there was a spelling error, or maybe it was a very old paper which was OCR'd and there was some error that the search engine could not pick up. So domain expert really need to sit down and evaluate each and every paper before they can move forward. And note that when we are talking about domain experts, they cost anywhere between $300 to $500 an hour. So you can imagine already how expensive that is. And there is the entire world to explore, right? So we cannot just go to each and every site that we think has potential and do some research over there. That's not possible, because it takes a lot of equipments, teams, again, domain experts who are charging $300 to $500 an hour, and we never know what is the ROI is going to be like. And lastly, historical papers are almost never used, is because you have more than 1 to 2 million archived papers. and some of them are not even really accessible because the search engines have not been adapted. So that's a huge problem. So more than 200,000 unused research papers from the past is what we found from NRCan itself. And they were talking about some other geographies like India and Europe, especially Italy, where these archive papers are almost never touched, is because they're not searchable. They just cannot use it. So the idea is to use some machine learning model to classify these research papers into different ore types automatically with a certain confidence. For example, iron, nickel, cobalt, etc., so that they can eventually be mapped to a certain geographic location with a certain confidence. And how do we do that? Um, so the problem formulation was, we take recent and archived papers from their library, which is called GeoScan. I'll talk about that in a bit. We'll put that into this, let's say, a magic ML model. Note that till now we are not sure whether this would work, right? And this model would give out some predictions saying that, okay, this paper is talking about, this paper can actually give out iron or copper or nickel. And there was an extra class called reject, that it's not talking about any of the ores or metals that we are trying to extract. Along with that, NRCan needed explanations. Note that they are not familiar with modern black box kind machine learning models, right? So they wanted explanation. They said that whenever your model makes a prediction, it needs to tell us why it did that. And without reasons, they would not 100% believe it. So I'll talk a little more about that, but that is slightly out of scope for this whole talk. So this is the whole setting. Again, just to reiterate, so we take recent papers, we take archive papers, we take whatever we can from them, put it in this ML model, which does not exist right now, but we are hoping that it'll learn some patterns from there, and it'll make a prediction saying that in this paper suggests that in a given geography there is iron present, and with a certain confidence, let's say 0.7, and copper is 0.2, nickel is 0.1. That was the formulation of this problem. But there are a lot of conditions that were given to us. Note that this particular project was almost $1 million project. It's quite big. So that means the expectations were very high, as well as a lot of constraints on us. So the first one is, explanations can be keywords or phrases. That means if given a paper, you extract snippets from the paper, or excerpts, which can be even one word long, and they have to be related to the predictions that the model is making, which I mentioned a bit earlier. And we were given only 1,000 training examples. Guys, some of you have just started your career in machine learning. Some of you guys are interested in moving forward. Note that data is something that no one will give you. Just keep that in your mind, and you have to work with as few data points as possible. So in this case, you can imagine $1 million project with more than 1 million documents with them, and they only gave us 1,000 training examples and 200 test examples, and that's what we had. They did promise that if we need, then they can give, let's say, 1,000 more training examples, but thankfully we did not need it. There should always be a way to control the model's precision. I'll talk a bit more about that. So when you're working on projects like these, mostly with consultants, they want some sort of control, saying that we need knobs that we can tweak so that the model behaves a bit differently. I'll show you how to do that. And the entire research paper content can be used for prediction. We can use whatever we want. Paper metadata was available, like geolocation, of course, because that's our end goal, right? And paper category, for example, geochemistry or geophysics. Just to give a little bit of background, geology has two parts. One is geochemistry, one is geophysics. We were not interested in geophysics because we were only interested in the chemical composition of the land. So hence we wanted to filter out all the documents by this category. Model precision should be greater than 90%. So it was a clear acceptance criteria set by them. Training pipeline should be reusable for other ores. That means now they want nickel, iron, and let's say copper. Tomorrow they can change it to cobalt, gold, and something else. So they wanted it to be a bit flexible. And what we had to deliver was a scientific report. We delivered a 120-page scientific report to them because those people are also scientists, not in our field, but at least they are scientists. So they want a full detailed report of what we did. They wanted the model to be deployed with REST APIs. so that they can access it from anywhere and plug it in their applications. They wanted a user interface to visualize model predictions as well as explanations, and a human in the loop setup. I'll talk a little more about that. This is something very popular. People who are going to get into the industry after a year or two, note that whatever machine learning model you set up, whatever machine learning project you work in, human in the loop is going to be very, very crucial in that. All right, I'll just take a quick pause and ask you guys if you have any questions. Feel free. I'll take, let's say, 2 to 3 minutes to take questions. Otherwise, I'll move ahead.
So I guess Soham has a question. Maybe
Yeah,
Soham, you can go ahead.
yeah. So, hi, sir. So, I had a question regarding one of the things that you said that the users can tweak the model's precision.
Right.
So, why are they always not using the best precision model?
That's a very good question. Maybe you just wait for a bit. I'll be on that slide, and maybe we can come back. I'll call you out, and then we can discuss that. I
Yeah,
have a
okay.
dedicated slide for that.
Yeah.
Yeah, perfect. So I think Arunim has another question. Arunim, please go ahead.
Yeah, hello, sir. Sir, I wanted to like get an idea if the ML model was also able to get a economic feasibility of the reactions as well.
Yeah, that's a brilliant question. Sadly, it did not. The economic feasibility is something that the domain experts have to figure out by themselves. Something that's a very interesting topic for people to explore, though. But we did not cover that in our research, at least.
Oh, okay, all right.
Perfect. So Ayushman, the last question Tushar has in the chat. He's asking why not geophysics? Why did you not consider the geophysics?
Because geophysics mostly involves instruments. What kind of instruments we are using, what kind of tools we have to use to go mine, right? But we are not interested in what tools do we use to go mine. We are interested in what is actually there in that piece of land. What is the chemical composition over there? What are the different layers in that particular part of the geography? So that's why we ignored geophysics. And plus, the domain experts also suggested that just filter out all the geophysics paper. We don't need them. Only geochemistry is required.
Yeah, I guess there is another question which you may want to discuss later also, which is, can you talk more about human in the loop? I guess this is a very interesting.
I'll talk about that later. I have one or two dedicated slides for that.
Yeah, perfect, perfect, Ayushman. Thanks.
Cool.
Okay, so I guess then we
Let's
can
move
proceed.
forward. All right. So part two is dataset exploration, dataset format. You guys are already familiar that whenever you start a machine learning project, you spend a lot of time with the data. That is exactly what you need to do. But what I'm also going to show you is a framework for working on machine learning projects, real world machine learning projects with time constraints. So when in the lab, you can play with the data set for a month and probably your prof will not complain. Maybe they will. I don't know. Depends on who your prof is. But still, but when you're working on a project, which is a 6 months project and there's more than $1 million being spent on it, then every day counts, right? You'll be questioned if you spend more than a week on just data exploration. So how do you make that efficient? I'm going to talk about that now. So the dataset format that was given to us, there were XML documents, XML documents that are a bit difficult to manage, but again, there are various parsers available out there which you can use to parse such documents. We had title of the paper, which was less than 30 words, abstract summarizing the whole paper, less than 500 words, full text of the article, metadata contained date of publish date when the paper was published, category, geochemistry or geophysics, area coordinates, latitude and longitude in this case, for which area is it actually talking about. That was very important for us. And labels. Again, labels were from none, like most of the papers did not have any labels because, again, I told you, right, 1,000 papers were labeled. Otherwise, we had iron, nickel, gold, so on and so forth. So we had some labels for these documents. Total number of documents were around 1 million in the whole database. But again, the training data set size was 1,000 documents. Here I show the train test split, 1,000 training documents and 200 test documents, roughly speaking. Right. Here I've also given the source. I'll share the slides with you guys so that you can go and take a look at that as well. The source, the dataset source was GeoScan. It's an archive of geological documents or research papers from Canada. So feature and attribute selection was the next bit. So, okay, we got the data. There are so many things. What do we select? So the first thing we did was some profiling of the data set. That means we checked like the title, right? We checked each attribute. We said in 98% of the documents, attribute is present. That means, okay, this is quite usable. 2% either absent or gibberish, because a lot of these documents were OCR'd, and if you have ever used an OCR, you know that it can introduce a lot of errors. Abstract, around 72, roughly speaking, 72% of the documents had abstracts. And again, the rest were either absent or gibberish, same due to OCR errors. Again, we are talking about archived documents, right? Even from the 80s as well. Full text present in almost all documents, but note that the documents before 90s, this is what we realized, document before 90s were very hard to even read because there were so many OCR errors. The formulas were wrong. It was just gibberish for us to use. So we almost in the very beginning, we knew that the full text will be very difficult to use in this project. Category we wanted to use, as I mentioned, geophysics papers we wanted to filter out. Geography, 70% of the documents had geotags. Geotags were very important. So we actually filtered first by geotag, because without geotags, we cannot create a heat map, which I'll talk about later. And date. Date was present in almost all documents, but it was never useful for us. We did do a little bit of experiments on trying to encode date in a certain format so that we can find some correlation, but it was just not useful. So we just ignored date. And some tools and libraries we used for that was Pandas. A lot of people use Pandas. Pandas profiling is a very good library which helps you profile your datasets easily. For visualization, I really like Seaborn, but there are a few cool new libraries out there as well. If you have anything that you guys know, feel free to put it in the chat and I'll be happy to look at them. Pre-processing. A lot of pre-processing needs to be done on your data sets. And I'm going to give you an overview of what are some of the pre-processing steps for text data. Sentence splitting, you take a long piece of text, split them into sentences. That's almost the first step that everyone does. Tokenization means you take sentences and split them into words or subwords. I'm not going to talk about subwords. It's an advanced topic. But in general, you split sentences into words. That's also called tokenization. Stopword removal. Stopword removal is where you are getting rid of very commonly occurring words like the, is, or if, let's say prepositions, etc., or domain-specific keywords or key phrases that you know are irrelevant to your model. So you create a dictionary of them and then you remove them from your data. It's called stopword removal. Lemmatization, I'll talk a little bit about that later. Lower casing is self-explanatory. And there are some others which are out of scope, for example, stemming, abbreviation normalization, regex normalization, so on and so forth. So these are some of the pre-processing steps. These are very standard. Almost every NLP library has some component or the other to do this. And I'm also going to talk about some of the libraries that I really like and I follow on a daily basis. So sentence splitting is very straightforward. Take a paragraph like this, and then you split them into sentences. You can do that either using some rule-based engine, which a lot of people do. I personally prefer using an unsupervised model to do this because then it is a bit more scalable. Tokenization is where you take sentences like this and split them into words. So here I'm representing them as a list of strings. So here, this is the first sentence in this paragraph. So it's converted into this is the first sentence, so on and so forth. Note that sentence tokenization and word tokenization have to be very sensitive to special characters or, for example, semicolon or smileys that people use these days or formulas in our case. So they had to be tweaked a little bit so that they can be used in our setting, which was extracting information from research papers. Stopword removal, again, a predefined set of words or phrases that we need to ignore. There's nothing that is exactly what it is. Some common ones are the, and so on and so forth. And given this example, in the first sentence, this is the first sentence in a paragraph, we will just get rid of the and in as well. It depends on how exhaustive your stopword list is. So once we remove all these words, whatever is left is our actual processed data set. I missed something. Lemmatization. Lemmatization is a process of converting words into the root forms, which comes from another concept in grammar, which exists in all languages, especially in Indian languages, which is called inflection. Inflection is where we take a word and either add a prefix or a suffix to that word to add expression to it, right? Some Indian languages are very, very rich when it comes to inflection. For example, all the Dravidian languages, Malayalam, Tamil, Telugu, Kannada, they are very, very rich when it comes to expression. Some languages like English are not that rich when it comes to expression. And some others like German, even if they are European languages, they are still very expressive. And what we need to do is, this process is essentially saying that if we have a word like playing, we'll convert that into play, which is a common root form. Plays will also be converted into play. Played will also be converted into play. And in case of some verbs like am, are, is will be converted to be, and so on and so forth. An example over here is the boy's car are different colors will be converted to the boy car be different color. So you see that we are applying some sort of a normalization on top of our sentence. If you are familiar with some computer vision processes, you also do something very similar to that. You apply normalization, but of course, the domains are quite different, but the process is almost the same. All right. So lowercasing, well, I'm not going to explain what lowercasing is. I think everyone knows what it is. Some tools and libraries that we find, at least I find very useful for each of these. As for sentence splitting, I like Spacey, but note that Spacey has very limited language support. But whatever language it supports, it is awesome. Stanza has 80 plus languages supported. So if you're working with some of the niche languages, especially Indian languages, you can use Stanza. NLTK is also there. NLTK has a way to train unsupervised models for sentence splitting as well. You can try that. We have tried that. We also use some of these sentence splitters internally for our use cases. Tokenizer, again, Spacey, one of my favorite libraries out there for NLP. Stanza, again. So Hugging Face, now a lot of people already know about Hugging Face. They have multilingual tokenizer support too. But note that to be able to use Hugging Face's multilingual tokenizers out of the box for word tokenization, you have to put some post-processing out there. If you guys are interested, you can ping me later. Lemmatization, again, Spacey and Stanza. Stop word removal, you can use Spacey, but it has, again, limited language support. So there's this library called Stopwords ISO. I really find that very exhaustive. They're doing a lot of research, very, very active community. So you'll find contributions almost every other day. So, and again, almost 80 plus languages supported. So these are some of the libraries. I'll share that with you later anyway. So I'll take another pause and ask questions. Please feel free. Janet, maybe if you can.
Yeah, so Soham, please go ahead, Soham.
Yes, so you said that unsupervised models are more scalable for sentence splitting.
Yeah.
So is it because of the large number of languages that you are supporting?
Yeah, correct. So when you're talking about multilingual models, right, multilingual use cases, you need to have some scalable approach because you cannot find resources to write rules to split paragraphs into sentences, right? So yeah, we use monocorp. Take a monocorpus and just train a model to learn how to split sentences.
Okay.
Yeah, perfect. So I guess Tushar is asking, you talked about remote languages. Tushar, would you like to unmute yourself and ask? But there won't be support for them. So I'm not sure what Tushar you're trying to say, but I'm sure what he's saying. You talked about remote languages, but there won't be support for them.
Yes. So I don't know, but maybe I think I understand what he's saying. So remote languages, let me take an example. Let's say Assamese. I would not call Assamese a remote language, but a low resource language. You don't find a lot of data, but you can always find corpora, monocorp. It might not be huge. It might not be 1 terabyte, but it'll be, let's say, 5 gigabytes or 8 gigabytes of data that you can get. So if you have an unsupervised model to train, let's say, sentence splitters, for example, then that would even be sufficient, right? So it will help you at least bootstrap your project. So from nothing, you'll have something.
Yeah, perfect. I guess we have for now. That's all. Yeah.
Okay.
So thanks. So yeah. So thanks, Shashmi. I think we can move. Thanks.
Cool. Let's move forward. So part three is agile model development. So note that till now we have not started developing the model, and all of this we have done the first 2 or 3 days of the project. Whenever you're working with machine learning projects, right, the philosophy should be, and machine learning projects in the wild, that means you have no idea whether it would work or not, right? So the idea is to be as agile as possible. So test your hypothesis as soon as possible and fail fast and recover faster. That should be the attitude. So I'll show a model to you guys. I followed this throughout my career. I've seen many people follow this successfully. And if you guys follow it, I'll be more than happy. So you start with your hypothesis. You hypothesize what you want to achieve from this. You test and validate your assumptions with domain experts or with the knowledge that you have. If you fail, you quickly iterate, hypothesize again, and test your assumptions. And this cycle should be done in a matter of a week or two, not more than that. So very quick assumptions, small assumptions, realistic assumptions, try, test, fail till you have something that works. And then once you have, this is called the feasibility analysis phase. Once you have something that works minimally well, then you go into the improvement hypothesis phase, right? So you think of how can I improve this thing that I know will work for sure. Then you start modeling even better. You do result analysis. And if the results are not acceptable, go back and keep hypothesizing, right? How can I improve the model further? Once you have acceptable results, then you deploy the model as soon as possible. Don't wait for the best model out there. If your acceptance criteria is 90% precision, the day you have 90% precision, you deploy. You don't wait for 98 and impress the customer. That's not how it would work. That you deploy your model, and then once your model is deployed and you have shared the results with your customer, then you can come back and keep improving the model and no one will complain. This is the model development phase. So some rules that I like to follow. Again, these are very loosely written, so of course feel free to change them. So daily progress updates have to be given. So every day you know what's going on. Weekly results should be shared with the stakeholders so that they know, they feel comfortable with what you're doing. Understand that you're working on machine learning. A lot of this they do not understand. Right? A lot of this is black magic for them. So you need to constantly share your results with these people who do not understand what you are doing, and which feels like magic. Short feasibility analysis phase, not more than 2 to 3 weeks. So that's why you need to buck up and to prepare. You need to use all the skills that you have learned in college or in the real world to make sure that you come to some minimal solution in a matter of 2 to 3 weeks. Never start without defining an acceptance criteria. So I have seen, and I've personally done it. So we would not define a concrete acceptance criteria for the success of the project, which in this case is 90% precision. And if that is not defined, then you are just shooting arrows in the dark, right? So you are extracting metrics which are not important. It's always very important to know which metric to chase after. Simple achievable hypothesis. Do not, so in the, at least in the feasibility phase, do not come up with the most complicated model design to test your simple hypothesis, and do never do that. Always be conscious about time. That means the improvement cycles might take really long. So always be conscious about time. If you know that you have done 2 or 3 improvement cycles already, results are acceptable, just move on, just go ahead. And then if you need to improve that further, you can come back there later. So be conscious about time. I'll give a real example of this, how we did it. So we started framing our problem like this. We knew it was a supervised problem. So this is day one. We knew it was a supervised learning problem. We thought, let's only use the title of the papers and use a very simple model like SVM, for which we have numerous libraries and numerous content on the internet. And we thought it would be sufficient to achieve the acceptable precision. We thought that if the precision is more than 50%, which in our case was not random, considering the number of classes, we thought we are in a good direction. We are heading in a good direction. We took 1 day to prepare the data and 2 more days to prepare a very initial report. So just 3 days, and we got a 68% accuracy, right? So we were like, okay, if we are getting 68% accuracy, considering the number of labels we have, this is not random results, right? So this is definitely something that the model is learning. So what we understood from here was that there is definitely some signal in the data that the model can pick up. Sometimes it can happen that there is no signal in the data that the model can pick up, or it is just too noisy for a model to pick up, right? So this is a proof for that. And in the improvement phase, we came up with a lot of hypotheses, like features from BERT like language models would improve the results, titles along with abstracts would actually have more signal for better results. Transformers instead of SVM on top would give better results. Precision can be controlled to get a 90% plus by setting a right threshold. So using the ROC curve. So I'm going to talk a bit deep in a bit detail about that as well. So, and we went from one hypothesis to the other, tried to prove it, get the results. As soon as we got the accepted results, we just moved forward. And it took us not more than 4 to 5 weeks to get there. Part 4 is model design. Here we talk about how do we featureize our data, how do we make model choices, how do we come up with architecture, and how do we control precision. So in our case, we started with title and abstract. Note that we process the data already. So following the data processing pipeline that I talked about. We took two kinds of vectorizers. I'll talk about them in a bit. One is called a sparse vectorizer, which gave us sparse vectors, and the other one is dense vectorizer, which gave us dense vectors. We concatenated the vectors that we got from these featureizers or vectorizers, and we fed them into our model. The model would predict a label, would give a label ranking as well as confidence scores. So this is the modeling bit. Note that there is the explainability bit as well. So we needed an explainability component which has access to our vectorizers, which has access to our model, and given a title and an abstract, for every predicted label, the explainability component will highlight keywords or key phrases in the title as well as in the abstract. Note that each predicted label will have a certain confidence. So that would help us somehow generate some sort of pseudo explainability. So we could never achieve real explainability, but this we called it pseudo explainability. And plus our customers or our domain experts were happy with that. So we moved on. So what is a sparse vectorizer? I'll give an example of a very simple sparse vectorizer, which is called a count vectorizer. Let's say the input text, a processed input text, is in the cold field. So it looks something like this. In the cold field are the words here. In is a stop word, so I'm just removing that. Then what I do is I take a vocabulary. So in this case, my vocabulary is of size 9. So I have 9 words in my vocabulary. A vocabulary is usually generated from a corpus. So you take all the documents that you have, process the entire thing, see how many unique words you have, and that is your vocabulary. So here, what I do is after I create a vocabulary, I arrange them in an order, which is from the top to bottom in this case. And you see that the is the second item in this vocabulary. So I mark that as 1, coal is the third one, and field is the fifth one. So I mark them as 1. Everything is a 0, is set to 0. And finally, I have a vector of size 9. And this is the sparse vector for my sentence in the coal field. Note that is a count vectorizer. If coal appears twice in the sentence, so the count will not be 1, it will be 2. Usually sparse vectors are really large. They can even go to anywhere between 100,000. The vector size can be anywhere between 50,000 to 100,000, depending on how large your corpus is and how large your vocabulary is. There are many other sparse vectorizers available out there. The one we used was semantic hashing or semhash vectorizer. The others are TF-IDF, hashing, simple hashing vectorizer, etc. There are quite a few available out there. Right. For dense vectorizer, we used a model called BERT, which is a very popular model these days. And it's called bidirectional encoder representation from transformers. Transformer architectures are quite popular these days because they are very linear in terms of compute time. And that's why they overtook LSTMs and bi-LSTMs, if you have heard of them. So I'll just touch upon the important bits that you need to know about BERT because it's a dedicated lecture by itself. But I think it'll give you a good idea of what happens. So we take a sentence like she is dash the ball, and we encapsulate it with sentence begin and sentence end markers like this. Then what we do is we represent the words in a certain format and feed it to a model which is called BERT. And what BERT does is BERT tries to do 2 things. One is it tries to represent the whole sentence in a vector which we will call CLS vector. In this particular architecture is 768 sized vector. and it will also try to predict the masked word, or the word that you omitted in the input sentence. So here the BERT model will try to predict what is this mask, and here it says throwing. So based on what it predicted and what was actually there, we will calculate a loss, and we'll train through back propagation. So this is how the BERT model will try to learn semantics in sentences for a given language, of course. Note that the CLS vector is a dense representation. So I'll just go back to my previous slide. The reason why they're sparse and dense is that in sparse vectors, a lot of these numbers will be zeros and only a few will be ones. That's why sparse vectors. In dense vectors, all the values will probably have some real number in them. And so they are dense vectors. So CLS in this case is a representation of or the overall meaning or semantics of the sentence. And during inference time, what you're going to do is once the model is trained, you just pass a sentence like this: that nickel is abundantly found in Quebec. You add the sentence markers, you feed the sentence representation word representations into BERT, and gives you a word representation. And that is your sentence vector in this case. Various other dense vectorizers available: Word2Vec, Glove, Roberta, GPT, Elmo, and there are more than, I don't know, 20, 25 different kinds of models that you can use. Feel free to go to Hugging Face. They have a huge exhaustive list. The classifiers we went for were SVM. Note that in the feasibility analysis phase, we tried with SVM already. We knew that we can get some decent results, but then we want to try a lot of other models. SVM, simple MLP, BiLSTM, Transformer, XGBoost, FastText. We went for all of them. And how did we figure out which model was the best? Usually, no one has a real answer, right? Which model would work the best? So what do? You do hyperparameter search. So we did exactly the same. Luckily, we had a lot of compute resources. We had many GPUs, especially the V100s, that are the very powerful GPUs as well. So what we did was, here I've given a list of hyperparameter tuning libraries that are out there. Some of my favorite ones are Dragonfly Search, which follows a Bayesian optimization method for giving you the best parameters. But there are many other simple techniques like random search or grid search that you can use. And what we did was we ran a lot of hyperparameters on our GPU cluster, and we just waited. Every time we would get a certain model that performs well, we would take that, do some manual testing on top of it, show the results to our customer, and then go back and run more experiments. Note that while these days people blindly go for deep learning models, assuming that they will give the best results, you will be amazed how well SVM or XGBoost or these simple models perform on such tasks. So do not get swayed away by the hip thing that is going on out there. Do try some of these simple models. They will surprise you. Precision controls. How do we do that? If you guys are aware of the ROC curve, what it does is it's a graph which you plot using the confidence score that your model predicts. And on your x-axis, you have false positive rate. On your y-axis, you have true positive rate, right? And on various different thresholds, you try to see what is your true positive rate and what is your false positive rate. So you go from the lowest threshold, which is 0, to the highest threshold, which is 1. And an ideal curve should be like this, the blue line that you see here, right? So the perfect one is the purple line, which you almost never achieve. But the blue line is what you are hoping for. So that is exactly what we hope for as well. So once you have a curve like this, what you do is you pick a point on this curve, which has the maximum true positive rate and the minimum false positive rate, right? You pick a point, which is usually the point that bulges out in this direction. So you take that point, and that point will be represented by a certain confidence threshold, right? You take that threshold, and then you see what is the precision of your model. So how would that work? So given a threshold, you reject all the predictions which have confidence score below that. You take only the ones which have confidence score greater than that, and then you calculate your precision. So you will know that by changing the confidence threshold, your precision would also change. This is how we control precision. And this is the knob that we give to our customers. And this is what they change to get the results that they expect. So in our case, what we did was we We controlled our precision. We set a right threshold by running some experiments, and we got a 94% precision. Of course, this was not in the first iteration. It took us like 3 or 4 iterations to get there. But a very, very important point to note, right? This is a power that you need to use very cautiously. That by setting a very high threshold, you will reject most of your examples. Your customer will come back to you and complain saying that your model is not predicting anything. You will go back to your customer and say, but whatever my model predicts it correctly, right? So this is an assumption. Sometimes your customers would not want that. Sometimes your customers would want high recall and low precision. They would want to extract whatever they can. Sometimes they would want high precision. So this threshold is something that you should always iterate with your customer or with the domain expert that you're working with. Some problems with neural nets. Again, I'm a big fan of neural nets, right? But they have some real problems. For example, to run something like this, you would want your confidence thresholds to be evenly distributed, right? But neural networks are by nature not like that. So in neural networks, the confidence scores are extremely skewed towards the extremes, right? So either towards 0 or towards 1. That means neural nets are overconfident almost always. So keep that in mind. So when you are trying to do something like this, where precision control is important, neural nets might not be the best way to go. So how do we run inference on a setup like this? So in our case, we pull documents from GeoScan database, we feed it to our model, we check the confidence threshold, and we check whether the confidence score is greater than the threshold. If it is, then we log results for future reference into our DB. If it is not, then we save results for manual verification. So this is where the human in the loop starts to come in. So once a document goes into a manual verification mode, then in our user interface, which I'll show you later, we had the option for manual domain experts to go there and verify whether the model was right or wrong. And then you can take all that data and retrain your model, go through the same cycle again. I'll just take a quick pause. I think we don't have a lot of time, so I'll take a very quick pause, maybe 2 or 3 minutes to answer questions.
No. So I guess, Ayushman, there is no lack of time. We can continue till 15, 10, 20. So don't worry about it.
All right, brilliant. Then I'll take questions freely.
Yeah, so I guess, are there any questions from participants? I guess Soham again has a question. So Soham, yeah, please go ahead.
Yeah, so if I remember correctly, any one document can have mentions of multiple types of ores, right? Like nickel, iron, copper, etc.
Correct.
So how are we calculating precision and recall in this case?
So in that case, so what we did was we did not have a multi-label classification, so multi-class classification model, right? We always predicted a single label with a certain confidence score. But what we did was to differentiate between that. Our domain experts had given us a list of filter phrases. So for example, iron would always come with some other ores. Gold will come with some other ores or some other metals, and copper would come with something else, right? So we had a list like that. So we use some of that to do some sort of post processing afterwards. Otherwise, we let the model learn by itself what to ignore and what to not ignore. So let's say multiple ores are present, so the model would learn how to ignore the ones that are not relevant.
Yeah, got it.
Yeah, Ayushman, there is another question from Tushar in the chat. He's saying you talked about fast text, but it is a word embedding, right? So how did you use it as a classifier?
So fast text, so what you do is you take the fast text vectors, which give you embeddings at a subword level, and you just add an MLP on top of it. You just add a layer of neurons on top of it, and then use backprop to train it. That's it. Fast text also provides some APIs. Fast text library provides some APIs for you to train text classification models directly there, but they are also doing exactly the same thing.
Yeah, perfect. So I guess, guys, any other questions? In any case, Ayushman, I think, at the end of the talk as well, we can just take some time and try to answer some questions. Thanks, Ayushman. So yeah, we can move. Thanks.
And I'll do something. I'll open up another question for the audience, and whoever answers this question even close to the correct answer, I'll give them a goodie, a neural space goodie. All right. So the question is, that do you think if we train a word embedding model, if we train a language model for a specific domain, in this case, let's say geology, then would it give better results? right? So, and I'm not expecting a very objective, very straightforward answer. I will try to find the closest answer and see who gets the best one. All right. Model deployment. So just training the best model is not the end of the story, right? So you have to deploy it somewhere. It has to be scalable. It has to be in a way that you can update your models and still the results will be fine. So that's why we use a few tools. I'll give you a big picture of how that works out. So we use some tools, for example, Docker, Kubernetes, and of course we have the human in the loop concept, right? Docker and Kubernetes are two things that I believe everyone in the current, everyone who's learning technology or working in technology in the current time should know. So you guys also try and learn and pick up these technologies as soon as possible. So our deployment strategy was that we'll have a front end. The front end was developed in using the MERN stack. The MERN stack is Mongo, React, Node.js, and Express. There's some of the frameworks that are available out there. Of course, the front end was packaged using Docker. People who are familiar with Docker, good. People who are not familiar with Docker, I'll give a very high level explanation of it. So think of Dockers as very portable virtual machines, right? Which actually run on virtual machines. So you package your application in this image called a Docker image, and you have all your libraries and tools, whatever you need to run your code packaged in there, and you save it as a file. It's actually a compressed file. And what Docker has is Docker has runtimes, which you can install on any operating system, any virtual machine, and your Docker image, your application can run anywhere. So that makes our lives very easier. So we don't have to worry about what the framework or what the platform is or what kind of machine I'm going to run my application on. If you have it Dockerized, it can just run on that. So makes our lives much easier. The model has to be wrapped in a REST API format. So we used Fast API for that. I am a big fan of Fast API, very good library, very active community. So, and GUnicorn again is something that you use to optimize your REST APIs so that you can handle a lot of requests in parallel. Again, Dockerized. We had the Geoscan DB. Geoscan DB is a third-party service that we used, and we had to do almost nothing for that. We just used their APIs to consume the documents. We had an application database which we used to keep all the results. We used MongoDB for that. NoSQL is again. I've worked on almost all kinds of databases, and I personally prefer NoSQL databases. Logging and monitoring. So whatever you're doing on the platform, let's say this front end or the back end, you need to keep track of them. You also need to monitor the health of the application, whether it is alive, whether it is dead. Is someone using my application or not? So all of that is done using this library or using this platform called Elasticsearch. Excuse me. And Kibana. Kibana is a tool to visualize logs. And it's a no code. You can use it in no code fashion as well. So you have drag and drop components that you can plug here and there and create your own dashboards, which you can monitor real time. So we use these tools for that. Again, we used managed services for both application DB and logging and monitoring. So what are managed services? So in the cloud era, you have to almost never deploy your own database in your own virtual machine. They provide managed services. That means they take care of scaling, they take care of where to host these virtual machines, and they will give you an entry point to these applications. So in this case, when we used MongoDB, we just took Azure. Azure has a managed MongoDB, and we use that. And why is it good? Is because it scales infinitely. So Azure makes sure that whenever you consume a certain amount of hard disk space, they would automatically increase that. So you never have to go and manage it manually. So back in the day, there were dedicated people who would do that. But in today's world, when there are so many startups and not everyone has the capacity to do it, managed services are the key. Logging, exactly the same. So we used Elasticsearch, has their own managed service, so we use that as well. And these applications are connected with each other. There are various ways in which you can connect services with each other. One particular way we went with is called pub sub. So I'm using these terms. I'm throwing it out there so that you guys make notes and go read about it. Because these are things that need dedicated lectures or a sequence of lectures, right? So the way we connected these applications is called pub sub. It's called publish subscribe, where it's like a mailing service. Each service is talking to each other by sending a message. So So let's say the front end wants to talk to the model. So it will send a message in a queue saying that give this message to the model. And when the model receives that message, it will process it and then put it back in the queue saying that give it back to the front end, and the front end will consume it. Same for the others as well. So we had pub sub services to manage all the different floating services that you see here. We wrapped all of this in something called Kubernetes. Kubernetes, it's, if I have to, I like this definition of Kubernetes. So it is the operating system of the cloud. So, and it makes your life easier to deploy application on the cloud. This Kubernetes is essentially a cluster of virtual machines, which you can scale separately apart from your applications. I'll not go into the details of it, but I'm a big fan. I think in the last decade, one of the best technical or engineering product that has come out is Kubernetes. Go read about it. So we wrapped everything in Kubernetes, but what are the UI features that were expected from us? Note that it is very important to build a model, but if it cannot be consumed by people who do not understand machine learning, then all your efforts go into waste. So we had these features so that they like what we did. A heat map was generated every time we would pull geoscan documents and parse them through our model. So it will produce these, like, this is not the actual image because I was not allowed to use the actual image, but something like this, right? So it will plot these heat map kind of a thing on top of Canada's map and say that these are the regions that you should be interested in. The ability to change the confidence threshold had to be there. So we added that too. Updated ROC curve for visualization based on the new results that we have. So every time we would pull documents, we have a new set of results. So we would plot the ROC curve again so that they can refer to that to select a threshold. And the ability to manually verify low confidence results. So we had a page dedicated for them where their domain experts can log in and go from one example, go example by example, and verify whether the model did a good job or not. Like, it was a very easy thumbs up, thumbs down kind of a button for them, right? So that was that kind of closed the whole human in the loop situation for us. And how do we roll out? Before I go here, which is very important. So the human in the loop is very important, but what is even more important is to understand what do we do out of it. So the humans are going to keep labeling your data, right? They're going to non-stop label your data. Do you think just by adding more and more data, you are helping the model learn better features? Sometimes that might not be true. Sometimes by just adding data, you are biasing your model. For example, if your labelers are only correcting one class only, right? Are only correcting one class label, sorry. That means, and you add that back to your database, right? And after 6 months, you train your model again. That means you have bloated one class label only. So your model is going to be biased. So you have to be very, very cautious about how you're doing it. You have to have data balancing techniques in place to make sure that your models are never biased. Or when you are actually adding examples back to your DB, right? You let the labeler know that, hey, this example actually adds no value to the data set. So even if you don't label it, it is fine, right? So some mechanism on top of it actually helps you create a better data set. All right. So once you have all that in place, then comes the time when you have collected a lot of data from your labelers. Your customer is happy that, okay, everything works fine. Now it's been 6 months already. I've collected a lot of data. I want to roll out a new model. I'm ready with my new model. Please give me a new one. So how do you roll out a new model? Something that I learned the hard way by making a lot of mistakes and talking to a lot of people. So I'm giving you out this information. Please keep that in mind when you are doing something like this. Every time you have a model which is in production, you never, never, never replace that model directly with a new model. Never do that. It will only lead to sleepless nights when your manager will ask you to go back and roll back everything. And that's not a place where you want to be. So what you always do is you start with adding the model into the cluster. So that means your model one is there. It exists and it works fully. It's fully functional. Your model two is also there. And your front end, what it is doing is it is doing something called a fire and forget, which is it is firing the request to model one and showing the results to the user, but it is firing the documents to model two, but it is not showing anything to the user. That means it's firing and forgetting. So what happens from that is the results that you get from model two can be visualized by your domain experts, and they get a sense of how good the new model actually is and how good it performs with real world data. This kind of deployment is called canary deployment, and there are various platforms and frameworks that help you do that. The way you actually roll out a model is that you reduce the traffic to model 1 by 20%, and you increase traffic to model 2 from 0% to 20%, right? So that means now in phase 1 you did fire and forget. In phase 2 you do 80-20, right? And show the combined results to your users. And then you get a feel of how the model is performing, how the new model is performing. And then you slowly reduce that. You slowly reduce the traffic to model 1, and at some point model 2 traffic will be 100%, and then you can totally get rid of model 1, and model 2 prevails. So the same thing you do when you have a model 3 or model 4 or model 5. You always follow a process like this, because this is a more stable and more, I personally think, is a more scientific way to deal with a situation like this, where you are taking observations, and based on your observations you are taking actions. All right. So before I conclude, I'll take or maybe I'll just conclude and I'll let you guys ask questions. So the whole project was a huge success at the end. My company generated more than $1 million in revenue from only this project. NRCan wanted to build a SaaS platform. It was actually so cool that they wanted to build a SaaS platform out of it, so that they could sell it to other countries. NRCan is using this for mapping nickel and iron mining sites in Canada right now as we speak. And almost 1 million untapped archived documents were used without any manual verification or any manual intervention. That is actually what made a huge difference for them. So I think that is it. Thanks a lot, everyone, for your time. And feel free to ask any questions you want. I think we do have some more time, so just shoot.
Yeah, so first of all, thanks a lot, Ayushman. It's a really interesting talk, and I also am very impressed by the amount of impact that it has caused. And seriously, $1 million, I mean, for a project which has so many different components, and I think it's really amazing. So I guess we do have like some questions from the audience. Maybe I think we can start with who we have first here. Janvi, maybe Janvi, you would like to start?
Yes, sir. Firstly, it was an amazing talk. Then I would like to guess the question, the answer to the question which sir asked. So you said that we can, train a word embedding on your corpora. So I think it would help. Why? Because what a word embedding essentially does is that. So, for example, when we have we have the glove word embedding. So the difference between the vectors, it would be, so the vectors representing gold and silver and maybe copper, manganese, iron, the basically the relation that they would incorporate in the glove embedding would be that these all are minerals, right? But if you will specifically train it on your data, then I think the relation that will also get captured is that iron, copper, manganese, they are found together. So I think it would help in your case. So for example, you have found a paper which has copper, manganese and other things, then maybe you can look out for papers having iron as well. So I think in that way it can help your case.
I think that's a very good answer. That's a very good answer. It is missing a very key component over here, right? Can anyone take a stab at it? And please feel free. There's no like, I'm not expecting you guys to give the spot on answer. So please feel free, right? It's an open space.
Yeah, so Soham, maybe you want to go next if you have the answer to this question, or do
Yeah, I
you
had a
want to?
question as well as I wanted to add a few things to this. So,
Mhm.
like say fast text is a like embedding process. So maybe we can pipeline fast text with an MLP and then it fine tunes that from the results of the MLP. So the embeddings that are learned are also learned in the context of how we want the results to be. And hence learning can also take over to the fast text. Unlike the like dense vectors and sparse vectors that we were using in this like research. Maybe
That's
that way it can help.
very, very interesting take on that. So you're saying that you will, so something that the people, like the BERT paper was also trained on something like that. So you have multi-objective training. So not only train on masked sentences, but also predict the next sentence. Sometimes you have a certain task as well, like NLI, for example. So you have a different task. The model is performing various different tasks while learning the embeddings. Very, very good answer. But again, there is one small thing that is missing, which is in the context. I'll give a hint, and I'll let like one more person try to answer this. So the hint is that note that we are not, so you're not training a language model on corpora, like a Wikipedia corpora, right? So you're training a language model on a very specific domain, which here is geology, right, or geochemistry. So do you guys think there is something missing? Right? That we need one more thing before we can actually train a perfect GeoBERT, let's say. So the first answer was by Janvi, right? Janvi, and the
Yeah,
second
so
was by
yeah,
Soham.
Jan, and second was the Soham, and there is another comment in the chat by Tushar. Tushar is saying the word embedding might not be trained on domain-specific words, so fine-tuning on the domain-specific documents should help in essence to capture the context of papers in this case in order to classify the documents better.
Yeah, I think agree. I think all three of you kind of gave an answer in the same direction, slightly different from each other. But the thing is, we tried it actually. We tried it, and it did improve the results, but not significantly. And we also discussed it with domain experts, and the reason why they said it did not work that well is because when you're talking about geochemistry, right, a lot of this knowledge is actually not. So when you're training these language models, these are masked language models, right? So you take at most 2 sentences, and then you kind of hide these words or mask these words, and the model tries to predict these words. But the relation between iron and gold might not be present in 2 consecutive sentences. It's something that you learn through the process. When you are studying geology, that's when you learn that these chemical compounds or these metals are actually linked together and they are found together. Sometimes they would occur in sentences close to each other, but sometimes they would not. And that's why that was our guess, that maybe either we need to increase the window to, let's say, I don't know, 3,000 words or 4,000 words, uh, and then the model would probably capture relations like that, or we need to figure out a way to induce this knowledge into the model while it is training. So there are ways, there are things that people have tried, like memory networks. If you have, I'll just throw these ideas at you guys, and you can go and read about it. There's a concept called memory networks. Memory networks is where you train a neural network and have a base of facts, have facts that the neural network can look at while learning patterns. So maybe, so it's our hypothesis again, maybe if you use something like memory networks, you can induce facts like this, relations like X metal is related to Y metal, and the model can learn from there. So that was again our hypothesis. We did not get time to do all that, but it was an interesting experiment. So I'll try. So thanks a lot, all three of you, for answering. So was the last person.
There is one more answer I guess in the chat, Ayushman, from Pratish. So he's saying we need to incorporate location and the type of geology present near the said minerals.
That's a wonderful point. I think that's also, so what you are essentially saying, that you will extract meta information from the text and then use that somehow as objective for training the model. Brilliant answer. Brilliant answer.
Yeah, so I guess Soham again has a point. So Soham, yeah, please go ahead.
So I was wondering that, like say fast text and all these word embeddings, they have like two kinds of things they try. So one is skipgram and the other is continuous bag of words.
Right.
So like you said that these minerals might not occur in close proximity of each other in the, yeah, say in the window size that you are specifying.
Correct.
But still, if the two minerals are occurring in the same context, so for example, I found and brackets this mineral in this location,
Mm-hmm.
then the embeddings that the model learns for these two minerals would be same or similar, right? So wouldn't that still work?
Yeah, I think that's something. I think this is a very hand wavy discussion that we are having right now. So we are talking about why is the model learning a pattern? Will the model learn a pattern like this? We don't know, but from our experience, what we think is that yes, it might work, it might just work, but the thing is that sometimes it is very difficult. So it's not like a man and woman kind of a relation when you are trying to find, right? So you are trying to find relation between, let's say, iron and gold. So what you are saying is that after training this GeoBERT, let's say, so I'll try to see what the model has learned, what kind of relationship the model has learned between iron and gold. So in that case, the explanation you will probably never find, is because these are very abstract, latent representations that you get, right? What you can do is you can use the model to predict something and then guess that, okay, now I see that, okay, probably the model learned this, and that is why I can conclude that it has learned something.
Yeah, perfect, Ayushman. I think that's a great interaction, at least with Soham himself. So I guess are there any more doubts for Ayushman?
Any other questions, people? I've made notes of, please tell me if I missed someone. Chanvi, Soham, Pritish, and Tushar. 4 of them. I'll get in touch with my operations team, and you guys will get some goodies from us. So, can
So I
you
guess
please...
there is a question from Tushar again. He's asking, did you put in place some threshold to keeping the model from getting biased by the human annotations, or what exactly did you do? If you can talk about it briefly.
Yeah, brilliant question. So there's a technique called first second distance. I'll touch up on that if we have time. Do we have like 5 more minutes? Can I take 5 more minutes?
Yeah, Ayushman, sure.
Brilliant. So there is a concept called first second distance. So when you have a classification model, your model predicts, or maybe just let me, do I have a whiteboard here? I should have a whiteboard here, right?
Yeah, you can get it from, if you use, I guess, the more, maybe it should be visible for you.
Okay. I don't know where the whiteboard is. Advanced share settings, no? Otherwise, leave it. I think I'll just try and explain it. I think we are. So what do you do with first second distance is, let's say your model is trained. Now your human annotator is sitting and trying to label the document, right? So you put a threshold not only on the confidence, but also on the first second distance, which is the distance between, or the difference between the confidence score of the first predicted class and the confidence score of the second predicted class. So in this case, if it is 0.8 and 0.6, sorry, 0.8 and 0.2, so there are 2 classes, so the difference is 0.2, right? So if there are 3, you can do that accordingly, and if there are 4 classes, you can do that accordingly. So we put a threshold over there, and whenever we have a predicted model, we take a new example that the model has never seen, we feed it through the model did not accept it, the model rejected it because the confidence threshold was set too high. Then we calculate the first second distance. So first second distance tells us which 2 classes or which 3 classes the model actually confused with, right? And then what we do is, based on that, we write a few very simple rules, whether we give a thumbs up or thumbs down. So we pre-fill the thumbs up and thumbs down for the annotators, and we tell them that adding this will actually add some value. So because the model is getting confused between class A and class B, because the distance is not that high, so that's why it is getting confused. So add that to your example. I'll add that to your data set. The model will probably learn some new patterns. But if the distance is already too much, then it is probably not going to add any value to your data set or to the model. So that's one technique that we use to kind of help the annotators understand that you should not add bias to your data set.
Yeah, so I guess that's a thanks from Tushar then. So are there any other questions, guys? Anyone? No? Okay, perfect. So if there are no more questions, Ayushman, then I think it was a really exciting talk. And I have noted down multiple points actually, for my understanding and for my learning as well. So there are at least 3 takeaways that I would like to take from your talk. Like one thing that you rightly emphasized, that there is never going to be enough data. And this is one thing that I have been repeating again and again and every talk. That like every interaction, that there is never going to be enough data for you guys, no matter in which domain you are operating. Some people think that okay, just because you're operating in NLP or CV, you get more data than 2 others, but I think this is simply not the case, and that is one brilliant point that was made by you. Other thing, I think you rightly put another point, that do not get swayed away by the fantasy of these deep learning models, right? So okay, it's good there that there are lots of fancy deep learning models are there. But just because deep learning models are there, just do not get carried away by them. There are lots of models, and for example, even to start with, for example, decision trees and all these models, there is a lot more explainability among these models than what you can get from the other models. So I think this is other take point. Other take point, of course, I think you rightly put it, that if you are building a deep machine learning model, and at the end of it, a non-machine learning expert is not able to consume that information, then this is good for nothing. All your efforts are good for nothing. So I think these are the 3 take points that takeaways that I would like to take from your talk. And I completely echo the point of several of the students here. that it was a really exciting and brilliant talk, and it was more importantly, like just at the level of what I expected. Also, I was really worried about like maybe I don't know if the students will be able to understand most of the things, because many times it gets too technical, and and especially we have to understand these are the UG students. Most of them are third year and fourth year students. Many of them, they have their first interaction with the machine learning. But I think I'm really impressed. I think you should be in academia. You should give these kind of talks more, and maybe I would definitely take this opportunity to invite you more and more wherever I can get an opportunity. So I think this is what like our students are commenting here. So for example, some of the comments: so brilliant talk. Tushar, thank you for such an enlightening talk. Janvi, I agree, very relevant and enlightening talk. So I think I just echo their point that this is just some of the comments that all they have. But as it was really great and nice to have you here. And with that, so thanks a lot. Definitely we will get back in touch with you. Please share the slides with us. We will pass those slides. And as I said during our first interaction itself, I would like to create a kind of a short assignment for them, where like of course for the bonus marks, if they want, they can just analyze the project, they can identify certain shortcomings, improve upon the model, and maybe I will get back to you with that. Except like if we have some interesting insights, maybe you want to comment upon them, and or maybe you want to hire them in the real estate
Sure,
down,
absolutely. Do keep in touch
down.
at least, especially, and thanks a lot, Janendra. Thanks a lot for all the wonderful words. I had a very good time. The interactions, especially, you guys are amazing, and I'm pretty sure that the class is filled with brilliant kids out there who are going to do a great job in the next few years. Shout out to Janvi, Soham, Pritish, and Tushar. Please get in touch with me on LinkedIn, because I really want to send you out the goodies, so that that's a gesture from my end to you guys for being more participative and getting involved in the whole talk. Thanks a lot, everyone. I'll
Perfect.
share
Thanks.
the slides as soon as possible, and have a good day.
Thanks a lot. Thanks a lot, Ayushman, and have a good day to you. And then thanks a lot for joining us. Thanks a lot, Ayushman. Have a good day. Have a good day, everyone, and thanks a lot for everyone joining. And definitely within few times you will have the next assignment and the details at least of the next assignment. So thanks a lot, Ayushman. Thanks everyone, and have a good day. Have a
Bye.
good day. Bye bye, Ayushman. Let's keep in touch. Bye bye. Bye bye.